Yeah, thank you for the kind introduction, and it's a great pleasure to be here. First time I've been in Taiwan, so I found it very exciting to be here. So the way that this session is organized is you will now get fairly extensive introduction about actually what's the basics of NMR structure calculation and validation, because we need to set the ground so that we are sure that we are on a common foot regarding a number of things. Then I'll show you how to use some of our related services on the WeNMR platform just for structure calculation, refinement, and validation. So it's really the basic structural biology by NMR, let's say, workflow. And then we will see how we are done with time, and if it's possible, I actually put up some data that you can download to try to use the portals in kind of, well, I guess half an hour or so. For this, we actually disabled, so I will show you how to use the SSO in principle, but for this session, we actually disabled the grid validation step. So for today, you will be allowed to enter in the system even without grid certificate, but that's temporary just for the workshop, but because from past experience, we know that this certificate business is always very tricky, and you always find a new unexpected problem showing up. Sorry. And then we resume. I will talk to you about paramagnetics in structural biology, which is kind of the specialty in Florence, and hopefully I will have saved enough time to show you about our tool for integration of NMR and SACS data, which builds, of course, also on the things that we've been lectured about today. Yesterday. Okay, so that's the general outline, so let's get started. This is just a reminder, I guess most of you are already familiar with it, of how the workflow for NMR structural determination is in NMR structural biology. And basically, even if I'm not stated this explicitly anywhere, we are talking about macromolecular structure determination. So it's either protein or nucleic acid structure determination, or possibly adducts thereof. But talking about complexes will be the topic of tomorrow mainly. And all of my examples are from protein NMR work, because that's the specialty of the lab. And there are also experts sorry, about nucleic acids in the WeNMR consortium. That's the University of Frankfurt, which is not represented at this meeting. So if you have some basic questions I can answer regarding nucleic acids, please ask me, but for complex questions we will have to get in touch with the real super experts. So as you know, you have your experimental NMR data. You have to do a number of things with them, which basically deal with assigning chemical shift frequencies. That is, you have to match each atom within your protein, let's stick to proteins, to a frequency in the NMR spectrum, be it protons or carbon-13 or nitrogen-15 nuclei. So each individual atom from each residue should be matched to a given frequency, and that's the assignment step. And then you also have to assign cross peaks, that is, interactions between pairs of atoms, which in Nosy experiment will correspond to distances between atoms. And then you translate this information into what we call structural restraints, which is a list of either distances or angles or other things. So we will have a look going on in the lecture. And these are then input into structure calculation algorithms that will produce an ensemble of structures that are compatible with your NMR data. And that's the part that the WeNMR platform is addressing as of now. And we also have something that addresses the assignment of cross peaks, but there's no time to demonstrate that today. And that goes actually into the CASD NMR initiative that Alexander mentioned yesterday, and I have a couple of slides also for that. So we do have some facilities to automate the step of noisy cross-peak assignment and therefore the production of structural restraints, but today we just assume that structural restraints have been, let's say, manually produced, as actually is still the case for the majority of structures that have been determined today. And we calculate the ensemble, then you have various checks that you should run, then you refine the ensemble, and you go into validation, which means basically you check the quality of your structure and decide whether it's suitable for publication and or deposition in the PDB. You know that protein structure determination by NMR is an undetermined task, because the number of experimental data you can get is actually relatively small with respect to the number of variables, that is the coordinates of the atoms that you want to fix to derive your 3D structure. And in addition to that, you also have a fairly large indetermination on the data themselves, which is given both, or is the result of both experimental error, of course, but also of some simplifications in the underlying theory that we use to be able to produce the structural restraints without too much hassle. But actually, we know that there are some systematic errors there. And because of these reasons, we produce what are called NMR ensembles or bundles or families. You will find different names in the literature, meaning that because we have few data with relatively large errors, we do not find a unique solution, a unique 3D conformation of your protein that satisfies the restraints, but actually you will find in your calculations multiple conformations that are all equally suitable, that equally fit the data. And so that's what makes the NMR bundle, and the bundle altogether is the NMR structure. So there's at least theoretically no clever way to just get one conformation. You do have to get a bundle, and that's why you actually end up depositing these bundles of 20, 30, 40 structures in the PDB. So this is the workflow. You have the sample, you do the spectra, you process, you assign resonances, you find conformational constraints, you calculate the structure. As you know, this is an iterative process, because having the structure will help you to find new additional conformational restraints, and also will help you prune errors in your original restraints and assignments. So you have to iterate several times between the 3D structure calculation and the analysis of the restraints. And so, and then at the end you have the validation. The kind of restraints you can get is relatively extensive, but in practice most structures still today are largely solved using distance restraints from nuclear Overhauser enhancements. Then you can get dihedral angle restraints from different sources, chemical shifts or scalar couplings. And then you have other kinds of restraints. I will not mention hydrogen bonds. These are residual dipolar couplings. We will mention those. And we have paramagnetics, which, as I mentioned, is going into a separate discussion. So there's a specific experiment you run in NMR to do this, to measure these nuclear overhauser enhancements, and it's a phenomenon whereby you excite the protons in your protein, and then you allow, during a so-called mixing time, an interaction to build between different protons through a mechanism that is called cross-relaxation. And at the end you get so-called cross-peak intensities, that is NMR signals that occur at the intersection of the frequencies of the two proton nuclei that are interacting with one another. And the intensity of the noisy cross-peak is, among other things, also dependent on the mixing time, so on this experimental parameter. So this is what it looks like. I'm pretty sure you are quite familiar. You have a diagonal, which is the self-interaction of protons with themselves. And then you have cross peaks. This is actually a slice from a 3D spectrum. So for the proton that's resonating at this frequency, you can see a number of different interactions, which are these balls that correspond at frequencies of other protons in the protein. That's why you need to have the resonance assignment, because then you want to, let's say, translate this into a distance restraint between these two protons. The physics is not particularly complex. I just showing this because I want to mention one of the systematic errors we have in this treatment. So if you assume that there are only two nuclei, two protons that are interacting, this is the equation that describes the physics underlying this cross-relaxation phenomenon. And actually this term called sigma is what is building the interaction between nucleus 1 and nucleus 2, because it's the non-diagonal term. And sigma contains a parameter which in turn contains the distance between the two nuclei. So because this is d squared and d is dependent on the third power of the distance, the effect is dependent on the sixth power of the distance between two nuclei, which actually has the practical implication that if two nuclei are farther than 5-6 angstroms, you will not be able to measure any interaction. But this is if there are only two spins in the proteins, but we know that there are many, so the matrix gets much more complicated, and you can write a more compact formula like this. For example, there's a description of the theory in this paper, but of course the theory is much, much older than 2004. And the implication with this matrix is actually that that you see it's completely populated with non-diagonal terms. So actually our idea that one spin is interacting with another is wrong, because all spins are interacting with one another at the same time. And so when you try to extrapolate the distance from a single cross peak, assuming that it corresponds to the distance between a specific pair of nuclei, that's actually an approximation, because it reduces all this big matrix to just one term. And it's what is called the isolated spin pair approximation. So you neglect the fact that your two spins are not only coupled to one another, but they are actually coupled to all the other protons in the protein, and you just treat those as if it were an isolated spin pair. So just two protons sitting in a empty space. Under this approximation, you can your experimental value is the volume or the intensity of the noisy cross peak, and you can relate that to the distance between the two atoms, as I said before, up to the power of -6, because it's 1 over r to the 6th. And then there's a function which can be basically parameterized. Then you assume your protein is completely rigid, and therefore this function becomes a constant which is identical for all protein pairs. So it's just one parameter that you need to assume for the entire protein if the protein is rigid. So there are a number of problems, as I mentioned already. The first problem is that proteins are dynamic, so you are actually measuring averages, which is fair enough. That depends on how big is the span of the dynamics, actually. If your average is similar to just one distance, or it's an average of a large variation in distance. And the other problem about dynamics is that it will also change this piece of the equation here, this function of tau c, where tau c is the correlation time for protein motion, actually. So if the protein is dynamic, this number is different for different parts of the protein, because some parts will move more, some parts will move less. And so this then becomes no longer identical for all proton pairs, and that in principle again complicates the analysis a lot. And actually, if you are unlucky and this number comes into a certain range of values, you can actually see your peak intensities disappear, even though the distance is within the range you should see an interaction for, because the dynamic is quenching the cross-relaxation phenomenon. The solution is that we neglect all of this, and we just throw in a constant, k, so we neglect all of these problems. We pretend the average is not important because the dynamics is just over a small variation of distances, and we also pretend that the function is essentially constant. We don't care about small changes here and there. But because we know that we are introducing errors, what we have to do is we have to give up the idea that we can actually measure the distance, and we introduce what you already probably know of as the upper estimation of distance or upper distance limits. So we say we use a single constant for all the proton pairs regardless of dynamics. We assume that we are measuring a single value rather than an average, but this single value that we are measuring is actually higher than the true distance. And it's the only way it can work. If you let your system then find a solution that satisfies a number of upper limits for the distances, then this will provide you with a structure if you have enough restraints. So the deviation of B from the true distance depends on local dynamics, because, as I said, we neglected the average, we neglected the local tau effects. But this, in principle, we don't know, so we don't know how large is this deviation. Because of various problems, we in principle, you could estimate a upper limit and a lower limit for the distance, but because of practical problems, normally people tend not to use lower distance limits, and that's because, for example, as I mentioned, if the dynamic is very, very unfavorable, even though your protons are close, you don't get the volume. So if you were to use a lower distance limit, you would say these protons are very, very far away, because otherwise I would see the interaction. But that's not true. It's the dynamics that's quenching your practical measure of the interaction. So this prevents you from using lower distance limits unless you go to much more complex computational approaches. So we call this the calibration curve, and the idea is that if you have a structure and you have real distances, so this is kind of a simulation, but you have different dynamics, your volume can actually span a relatively large range of values, your intensities, at fixed distance because of these various effects, plus the experimental error, of course. So you want to have a calibration curve that sits on top of this distribution of volumes, so that for a given volume you will get a distance which is for sure larger than any of the true distances that correspond to such intensities. Okay, so if you for example take this value here, the volumes that are larger than that intensity all belong to pairs that are at smaller distances than what you obtain from the red curve, which is 4 point something. So if you are at 3, you will get a volume of, you may get a volume of this intensity if your real distance is 3, but you will use 4 nevertheless. So that's the idea. Whereas if you go above 4 as a distance, you are not getting any volume that is larger than this. And so if you would put your curve like here, then you are really getting too much larger overestimates, and this is bad for your structure calculation. So you want the red curve to be as close as possible. This you can do manually or you can do automatically. That depends on actually the software you are using. Some software will do the calibration automatically if you say that your reference distance is a given value. Some other softwares will allow you to actually play with the curve. There's an alternative solution that is less labor intensive. You just say, you just categorize your peaks depending on the intensity into strong peaks, medium peaks, or weak peaks, and you allow a upper distance limit that depends on the class. So you don't have to think very much. You say if my peak intensity is larger than 500,000, then it's a strong peak. If it's lower than, I don't know, 10,000, it's a weak peak, and in between it's medium. And you just assign the upper distance limit to be either 2.7 or 3.5 or 5.5. The lower limit is 1.8, which is the sum of the van der Waals radii, so it's really not informative. Of course, if you go check in the literature, you will find very different numbers for these different classes depending on the author. The other notorious problem is spin diffusion, where you have a relay of interactions. So if you go into, we have this spin pair approximation, but actually we know that there are more spins. So in favorable cases, you can actually have multiple bodies interaction, like 3 atom interactions, where you get a magnetization, an interaction between A and C, but you can also get an interaction between A and C that goes via B. So A is interacting with B, and B is relaying this interaction up onto C. So you have a direct interaction, and you have an indirect interaction, which is called spin diffusion in the NMR jargon, via the third spin. And this interaction is actually making the intensity of the signal involving A and C higher than it should be in the 2-spin pair approximation. So if B were not there, A and C would have a given intensity, but because now B is there and you have an additional contribution, you get a larger intensity of the signal, which means that because the intensity is higher, the system will try to push the atom closer. And that goes exactly in the opposite direction that you want the things to go to, because you actually want to have larger distances, because you are saying that you will be satisfied if your atoms are closer than the threshold. So if you have a larger threshold, you just lose in resolution, but if you have a tighter threshold, that is the case here, you're actually getting problems because you are getting non-physical distances between atoms. And this is very difficult to correct for unless you explicitly account for this kind of phenomena. But if you stick to the 2-spin pair approximation, the only thing you can do is throw away the peaks. And actually, when you go and do these automated calculations, which are fully automated, as I will mention in this case, the NMR thing, this throwing away of peaks occur quite often. If you actually go into the detail of how the calculation was run, you will see that these programs are consistently throwing away peaks just because they think they are pushing the atoms too close to one another. And this is something that actually people often neglect when automated things are run, but it can be actually used as a quality measure. So in short, just to recap, this is the longer part, okay, just because these are the most important restraints, the rest will be shorter. NOEs between protons are measured by 2D or 3D NOEs spectra, where you relate the volume to the distance via a very simple relationship, which is we assume the volume is equal to k, a given constant, divided the 6th power of the distance between the two protons. You cannot use this approach to derive exact distances, for example, because of local dynamics, and that forces you actually to use not exact distances, as I said already, but upper distance limits. So you can do the calibration, or you can do the restraint classes. That's the same. That's two different things, two different approaches to get to the compiling a list of distance limits. And those are actually what you feed the structure calculation programs with, as we will see, hopefully before lunch. And then you have these so-called spin diffusion effects, which are a problem, and you can deal with them essentially only by removing peaks that you suspect are significantly affected by spin diffusion. Just a first mention of paramagnetism. If your system is containing a paramagnetic metal ion or a paramagnetic spin label, for those who are using spin labels, you will get a contribution to relaxation from paramagnetism. So there's an interaction between protons and electrons sitting on the paramagnetic center. And this interaction actually has a significant effect on NOE intensities, in that it makes NOE intensities much lower than they should be. And again, this is distance dependent. And this time we are talking about the average distance between the two protons involved in the interaction and the paramagnetic center. And you can actually see this plot here, which tells you in logarithmic scale how much the intensity is decreased as a function of the average distance from the metal side. So if you have at 4 angstrom from the metal side, this relates to a very specific protein, is 4-iron ferredoxin, because of the effect also depend on electronic properties. So you can get reductions which go from 100-fold to 10-fold to essentially nothing at farther than 6 angstroms in this case. Oh, I took the wrong. Okay. Chemical shifts and backbone conformation. So this is for NOEs. The other important source of structural restraints is chemical shifts, because chemical shifts provide you insight into the secondary structural elements where your atoms are sitting, and this is a very renowned effect since the early 90s. So this is an observation that's more than 20 years old, and originally this so-called chemical shift index was proposed, where the idea is that because, for example, you look at the H-alpha chemical shift, this sits in different ranges if that residue is in a beta sheet or in an alpha helix. And you see here that this effect is actually amino acid dependent. So for some amino acids, you actually have a more or less significant overlap between the ranges into the different types of secondary structures. So the idea of the chemical shift index is if you have a stretch of residues which all fall in the range of alpha helix or all fall in the range of beta sheet, you can actually make a plot like this. So if it's positive, meaning the chemical shift value is larger than the average, then it's in a beta sheet. If it's negative, so the chemical shift is lower than the average, it's in an alpha helix. And if you have a continuous stretch of residues that are all negative, then you are sure that's an helix. Or if you have a continuous stretch of residues that are all positive, then you are sure it's a beta sheet. And if you have one residue here, one residue there, then you cannot really say anything. And that initially was proposed for protons, but actually carbon chemical shifts are much better for this task, because the separation in ranges tends to be larger, and in addition you can also you can complement the C alpha data with the C beta data. So if you have an internal consistency between C alpha and C beta, that's reinforcing your per residue assignment of secondary structure. I'll come back to this shortly. The other way to identify backbone dihedral angles, that is secondary structural elements, is by measuring J couplings, especially what are called 3J couplings, so couplings between atoms that are separated by 3 bonds, such as in this example. You can actually you can measure 1J and 2J couplings, so couplings between, for example, carbon and hydrogen, or between 2 hydrogens that are separated only by 2 chemical bonds. And you see, if you are using heteronuclei, you can measure a number of these. So you can measure carbon-carbon, you can measure carbon-proton, you can measure carbon-nitrogen, 1J couplings, or you can have, again, carbon-nitrogen 2J couplings, and so on. But the 3J couplings are most useful for structural determination, because you can relate them to the dihedral angle that is intervening between these 3 bonds by means of the so-called Karplus equation. Now, this was a standard way to measure dihedral angles up to, let's say, the 90s, but now everybody is doing predictions based on chemical shifts, which is an extension of the chemical shift index concept that I was mentioning before, but with a growing database of protein structures and NMR assignments. As of the late 90s and even more in the first decade of the 21st century, there are more and more programs that are robust in taking information from databases, so PDB and biomagnetic resonance bank for the chemical shift assignments, and use the contents of the database to look at your own chemical shift, so for a system with a known structure, and make a dihedral angle prediction. And this is very useful because it has various advantages with respect to both the CSI and J couplings. With J couplings, the advantage is you don't take additional measurements, because you just take the chemical shifts from your resonance assignments that you have to do nevertheless. And with respect to the CSI, the dihedral angle values that you get here are much more precise than the generic assignment to either alpha helix or beta sheet. Here you are really getting values for the angles. So the first popular program was Talos, and now there's a so-called Talos Plus version, which is relatively recent, which is using an extended database and also has a an artificial neural network engine to support the predictions, and the error rates are of the order of 1%, as you see here. So it's pretty good predictions, I would say. And this is also available via the platform, the WeNMR platform. There's a specific portal for this program, which does not require the grid certificate because it's a very fast calculation. It just takes a few seconds and it's done. So I'm not gonna demonstrate it, but please note that it is available. And there's also another program which is based on largely similar principles, which is the random coil index program, which is useful because it also gives you a prediction of local flexibility. So here you are getting the dihedral angles and the prediction of how much the protein is locally dynamic. And this is developed by the Wishart group in Canada, and it's also available via the WeNMR platform. So you can do both predictions if you wish. Residual dipolar couplings are due to the orientation of is another kind of restraints, and it's due to the fact that if the protein is partially oriented in solution, you do not get averaging of dipolar interactions. So you have what is called the residual dipolar coupling, which actually depends on the orientation of the protein with respect to the to the magnetic field. This is particularly pronounced in paramagnetic metalloproteins, or you can make it significant in diamagnetic, for diamagnetic proteins if you use what is called an orienting media. So you take a solution where you have something that is strongly aligning with the magnetic field. If you dissolve your protein in that medium, you get non-specific protein rod filament interaction. You can do this in different ways. For example, viral particles are particularly popular and easy to use. So you get non-specific interactions between the protein and the orienting agent, which in turn makes the protein partially orient with the field, because this thing is strongly aligned to the field, as the picture depicts. The protein is interacting with this, so it gets partial alignment to the field, and you recover some of this effect, where basically you can measure the 1J, for example, the 1J split in between, the 1J coupling between proton and nitrogen, and this contains also an effect that depends on the angle between the magnetic field and the NH bond vector. So you can basically measure this angle here. You just need to measure the J coupling in the presence of the orienting media, and in the absence of it, you take the difference. What's left is the effect of partial alignment. And this is a very accurate measure that you can take. And so these are the equations. You will find them in any good recent NMR book, actually. As you see, it contains some terms that describe these D parameters, describe the extent of alignment, and then you have this angular parameter which tell you about the angle with the field and how it's oriented also in the XY plane. And this effect is actually very sensitive to dynamics, and this is something that we will be exploiting in the MaxSoc application that we will see after lunch. So now let me just go quickly through validation as well. Okay, these I already mentioned. You not only use NMR restraints in your NMR structural biology calculations, because you have, as you know, you have a number of terms that keep a protein together, which is, for example, bonds or bond angles, which actually NMR cannot provide you an insight in, because, for example, bond vibrations are way too fast on the NMR scale, and you are only ever measuring the average that becomes from, that is made from the vibration, and this similar concept applies to the angle. So actually, you cannot measure these parameters, and so you have to, let's say, simulate them by using an external force field. So in a way, you can say this is molecular modeling, which is driven by the NMR data, because you are assuming a lot of things. You are also assuming electrostatic interactions that, of course, you don't measure by NMR, according to an external force field. And because you cannot, as you know, we cannot yet use force fields to fold entire proteins, you need the NMR data to drive the folding under the force field. And the way this is done is that you have your ordinary force field terms, so to say, and then you just add another so-called pseudo-potential that represents the NMR data. And for this, you can use any standard molecular force field, charm, amber. So the way you represent the data is typically by using parabolic terms, where you have a range of allowed values, so no energetic contribution if your distance between a pair of atoms is in between the lower and the upper distance limit. And then you get a parabolic contribution to the energy, as you see here from the equation. If your distance is either too short, this actually will be soon going into van der Waals repulsion, so it will actually become rapidly much steeper than this. Or you just get this parabolic term, which is trying to bring the atoms back close to one another if your distance is exceeding the upper distance limit that you imposed. You can do similar things for all the various terms. If you have residual dipolar couplings, you can actually provide, you can actually instruct your system to basically do the fitting, and you enable a tolerance. So at each step of molecular dynamics, the software is fitting your residual dipolar coupling data again within experimental error. Then you get 0 if the difference is smaller than the error, or you get an energetic contribution if the difference between calculated and experimental values is larger than the experimental error. So if you get a contribution to the energy, of course you get a force which will try to bring back the system in order to improve the agreement with the data. And a very popular approach to calculate NMR ensembles is by doing this so-called torsion angle dynamics. So you don't represent the protein in Cartesian coordinate space, but you represent the protein as an ensemble of completely rigid bodies, which correspond to parts of the backbone or to parts of the side chains of the various amino acids. And you just assume that the degrees of freedom are the dihedral angles intervening between subsequent rigid blocks. And this is much faster than the normal molecular dynamics in Cartesian space, because by playing this trick of having rigid units within representing the protein, you greatly reduce the number of degrees of freedom. And this is also another concept that is relatively old now. The issue with torsion angle dynamics is that you also want this calculation procedure to be fast, because as I said at the beginning, you have to iterate through cycles of structure calculation and reanalysis of restraints. And so you want your structure calculations to take minutes rather than days, which means that actually in practice you are going to simplify also the force field parameters, or for some programs you may even neglect altogether some of the terms. For example, the Cyana program, which is one of the most popular ones, is completely throwing away the electrostatic interactions. They're just not represented in the program simplified force field. So so we are using a force field, but it's not complete, or it's simplified. Simplified means we are taking into account a smaller number of interactions than the program should. And this is, together with the use of torsion angle dynamics, motivated by the fact that we want the structure calculation to be really fast, so that you can run it quickly and then look at the structure and see if you have error in your data assignments, correct the errors, rerun the structure calculation, and so on. And if you have gone through this process, which is actually quite painful often, it can take several weeks. And during these several weeks, you will spend 90% of your time looking at the spectra, and only 10% of the time is going into the actual structure calculation. But the result of this is that the quality of the structures that you obtain in this way is often poor, because you don't get a good representation of the typical features of proteins. So you don't get charges that are correctly paired, you don't get enough hydrogen bonds and things like this. And the way you correct this is by doing this so-called energy refinement. So if you take, for example, I will go into slightly more detail shortly. If you take the Ramachandran plot appearance, which is probably known to all of us who are checking protein structures, you know that your amino acid backbone should be adopting given conformations, which are represented by the Ramachandran plot. You actually can measure the deviation of the Ramachandran plot of your protein with respect to expectations given what you see for high quality X-ray structures, which would be the line here. And the red is what you have in the database. So this is measuring standard deviations. So you see that the content of the PDB database in terms of NMR structures as of 2004 were as much as 5-6 standard deviations worse than what you saw, what was available in the database for high quality X-ray structures. So the distribution of backbone conformations within the Ramachandran plot when looking at NMR structures was much more dispersed and occupying forbidden regions than what you saw in the X-ray structures available at the same time. But actually, what these people demonstrated, among which Alexandre Bonvin, by the way, was that you can actually energy refine these original structures, and you can get a significant improvement. You see 2-3 sigma deviations of improvement. So still worse than X-ray structures, I have to say, but the improvement is dramatic just by applying relatively simple energy refinement protocol. And you can use different types of protocols. Which can be based, for example, on molecular dynamics or on other approaches, such as statistical potential or mean force potentials. You can call them in different ways, where again you see this tremendous effect in, for example, in the way you improve the Ramachandran plot appearance, and your original data violations remain pretty much unchanged, or they can actually improve a little bit. So this is just to say that the structures you obtain plainly from the NMR structure calculation are typically energetically not optimized because of the simplifications in the force field. And because it's just yet another computer calculation, which is going to take something like 1 day in the worst case scenario, after you spent 1 month looking at the spectra, it's very worthwhile because, well, it's not going to change dramatically your structure, but it's going to make it look much better for people who are looking at these kind of parameters, which in principle measure how likely is the fault that you, at the end of your structural determination project, have obtained and deposited in the PDB. So this is within the WeNMR platform, we developed a portal again, as Alexander mentioned yesterday, for doing this kind of refinement, which is carried out in explicit solvent, which is another limitation of the normal structure calculation algorithms, is that they do not include the solvent again, because if you have to put many molecules of solvent there, this is going to slow down your calculations. So what we do is we take the structure that is being, or the bundle of structures that is being produced by the structure generation program and the restraints, of course. We take the structure, we put it in a shell of water, then we minimize the waters around the protein, and we minimize the protein and the water together. And then we heat the system, so we give the system the freedom to move, and you can go up to 300K, or there are other protocols that we have tested. You can actually go higher, even up to 500Ks in the simulation. The protein will not unfold because you have the restraints, and the restraints keep the protein together. So even if you push the temperature very high, you don't see unfolding because the restraints prevent the protein structure to completely open up. So you run some molecular dynamics in water at relatively high temperature. Now 300 is not so high. Then you cool the system again, you minimize, and this is your refined structure. I will give you a look at the interface, so we can skip that. So as you see, the structure doesn't look terribly different. This is gray before refinement or black after refinement, so the structure is pretty similar, but you can show that you improve on various things. Contacts, typical output of NMR structure calculation programs have a lot of atoms that are too close, and this is because they use simplified van der Waals representation, again, to make the calculation faster. Ramachandran, rotamer distribution. Rotamer is the conformation, assesses the conformation of side chains, and there it is known that NMR is doing a poor job because many side chains, for example, are solvent exposed. You don't get many NOEs for those. And therefore the conformation is randomly generated basically by the structure calculation program. So your rotamer distribution is way off what it should be based on the statistics of other structures. Let me just go slightly more in detail about the various parameters that we use for validation. You have two grand categories, what we call knowledge-based, which are parameters such as those that I mentioned several times already, that are based on comparing your structure against what you see from high-quality structures. Of course, high-quality structure is an entirely arbitrary definition, but typically people take as a reference X-ray structures with resolution lower than 1.5, 1.2. That is arbitrary again. So you see, for example, how many residues in the Ramachandra, in the allowed region of the Ramachandran plots you see in these structures. You make statistics, you have several, so you can compute the entire distribution. Then you calculate the distribution in your structure, and you say, is this the same distribution or is it shifted the average is not corresponding. So, for example, high-quality structures have 98% of residues in the best regions of the Ramachandran plot. My structure has only 85. That's a problem, or at least that tells you that your structure does not look like a high-quality X-ray structure. And you can do the same for various properties. You can take the number of hydrogen bonds, or you can take the density of your protein, the tightness of packing. We will have a look now. And then you have database parameters, which I will not describe today because that would take another day on its own. That is, how do you quantify how your experimental data match the structure? So we all know about NOE violations. You count how many these upper distance limits are actually violated, so the corresponding distance is too large in your final structure. But you can do much more elaborate things to quantify in a statistically sensible manner the agreement between the data and the structure. So the Ramachandran plot, you know, bad contacts I mentioned. The two atoms get too close to one another, their van der Waals spheres overlap, and you can easily assess that. And as I said, many programs to speed up the calculations reduce the van der Waals interactions. Side chain planarity is another issue, but that's actually not so common for NMR structures because typically this is a rigid block, and so your structure calculation program will always keep the side chain planar. But then when you go into the let's say the refinement, if you actually have some local problems with the NOE network, you can get distortions. Bonded geometries, again, when you do the refinement, sometimes you can get inversion of chiralities. This is, I have to say, now very uncommon. It used to be more common when the force fields were less accurate than they are today. Whereas rotameric states are a very common problem in NMR. You may even find some residues in eclipse conformation, but it's actually more common that because different amino acids have different preferred rotameric states, it's actually much more common that the NMR structure provides you with one of the less favored rotameric states than what you expect for that given amino acid type. And you can conveniently look at rotamers in the so-called Janin plots where you plot Chi1 and Chi2, and you get allowed regions. So this is essentially the same idea as the Ramachandran plot, but for amino acid side chains. Z-score is the common way how you quantitate the deviation between your protein and the distribution, and the reference distribution for the PDB, for example, where basically you have your own value that you measure, for example, the number of Ramachandran, of residues in the best Ramachandran regions for your protein against the average that you see for the reference high-quality structures divided by the standard deviation of your reference distribution. So Z means how far away you are from the center of the reference distribution in terms of, or let's say normalized by the width of the reference distribution itself. Because of course, if the reference distribution is very narrow, even if you are just a little bit away, then it's a problem. If your reference distribution is very broad, then you are a little bit away, but that's not statistically significant. So Z tells you how many sigma deviations you are away from the center of the reference distribution. And you know that if you are 1 sigma away, it's slightly over 60% of chance to be there by chance. And if you are 3 sigma away, it's 99.9% that is a mistake, let's put it this way. Of course, it doesn't tell you it's a mistake. It just tells you this is strange with respect to this distribution, so in principle you should go there and double check why this has occurred. Oh, one of the easiest, I will just mention one parameter for database parameters just to show that there's something more than just violations, and for example, completeness. So if you know the structure at the end of your procedure, you know all the proton pairs that are close to one another within a given threshold. So you can compute how many of these distances you actually detected by observing NOEs with respect to the total number of closed in space hydrogen pairs that you have in the structure for which you would expect an NOE. And if, for example, you use a 4 Armstrong threshold to decide that if the proton pair is within 4 Armstrong, I should see an NOE, and you go compute the completeness for the structures in the PDB, you see the average is only 44%. So you're likely to basically measure less than half of the NOEs in principle you could measure. And you see it's also relatively broad, but of course if your completeness index is only 20%, it means that you did a poor job, basically. If it's 60%, you've done greatly. Let me just skip over this. I want to mention the NMR just because it provides some insight. As Alexander was mentioning yesterday, we recruited different software developers that develop automated software, and this software is taking care of all the steps in an automated manner of all the steps from the NOEs assignments. So they identify the peaks, they assign them to the protons, they compute the structures, they correct errors if there are any, and they automatically produce a final structural model. Then we have in the hidden somewhere we have the true structure, and we make a comparison. So we have a measure of accuracy, which is pretty straightforward. Is the root mean square deviation, so it's the coordinates deviation between the automatically generated structure and the reference manually solved structure, assuming that the manually solved structure is correct. And we set an arbitrary threshold. We say the structure is good if it's below 2 Armstrong over MSD. This is another similarity score. We don't go into the detail now. And this box actually is containing 90% of all the results. So make the statistics over all the 10 targets that each of this program was run for. The box contains 90% of the results. So you see this is very tight, this Sayana algorithm. It's very tight. It means that all of the structures are very close to what is the true reference structure, except possibly one exception. The whisker is the farther away outlier. So you see some of the programs do very well, and some of the programs are actually relatively poor. And this is chemical shift Rosetta, which is one of these programs that is using only chemical shift data. It doesn't use NOE data. So the first 4 programs use NOE and Talos predictions to calculate the structure. These other 2 programs use a combination of chemical shift predictions first to let's say, get initial structural models, and then they filter them based on the agreement with NOE data. And these other programs here, they just compute on the basis of chemical shift predictions alone. So they do some fragment picking from the database, and then they recombine different fragments in order to maximize agreement with chemical shifts. And you see they do very badly. So this tells you that for the current state of the art, you have to use NOE data. You have to use these upper distance limits. And if you use them and they are of sufficient quality, you can actually do pretty good in terms of doing things automatically rather than manually. Then you go to check quality, and we check out the scores that I was mentioning now. For example, this is clash scores, and this is the Ramachandran plot distribution. And what is actually surprising is that these programs, this CS Rosetta program, for example, that I remind you was the one who was doing worst in terms of being similar to the reference structure, is actually the one that has the best quality parameters. You see these z-scores are positive, which means it's actually better than the average of X-ray structures, whereas typical NMR structures are worse, the score is negative, than the typical X-ray structure, which comes at 0. What does this mean? It means that you can have a very high quality structure based on the knowledge of what a structure should look like in terms of Ramachandran, rotamers, and so on, and it can be wrong. These structures are essentially all wrong except one. Okay, they can be as much wrong as 10 or 15 Armstrongs away. But yet, in principle, they have the best quality if you don't take the data into account, if you just look at these parameter distributions. And why is that? You can think, even if the prediction is just a completely unfolded polypeptide, that's not going to satisfy the data, because the data tell you that the protein should wind up and bring atoms together close in space. But if your random coil locally has always the best possible conformation for that amino acid, you are getting exceedingly good quality, as here, but very poor agreement with the data. So even though I did not discuss data parameters today, I just want to give you the message with this, that data parameters are very important, because if you don't look at the data, you don't get the right structures. And you can actually look at the correlation between scores, and they're actually pretty much independent of one another, which means it's worthwhile to check all of them. You get some loose correlation between the backbone Ramachandran and the clash scores. So it means that if your backbone is good in terms of Ramachandran plot, you get better quality in terms of forbidden atom contacts. There are less of this. This is reasonable because you know that one of the basic physical reasons why the Ramachandran plot exists is because that distribution minimizes the number of unfavorable interactions between atoms. And so it's logical, I would say, that there's a loose correlation between the two things. Of course, this is measuring also for the side chain, which is not included in the other score. So after this longer than